Bismillahirrahmanirrahim. Sallallahu alayhi wa alihi wa sallam. Allahumma rabbi zidni ilma. Sallallahu alayhi wa alihi wa sallam. Ameen. Alhamdulillahi rabbil alameen. The topic of this lecture is important concepts of parametric equations of differentiation of P3. Parametric equation means two equations connecting x and y, and both x and y depend on the third variable, either theta or t. Like in this example, both x and y depend on theta. And this is the formula of the gradient of parametric equations: dy upon d theta upon dx upon d theta. An important advice for me and for everyone: we must be good to others. When both x and y are given as a function of a third variable t or theta, like this, both x and y are given as a function of theta in this example. In this example, they both are given as a function of t, and this example, they both are given as a function of t, where theta and t are known as the parameters, and the two equations are called the parametric equations of the curve. So these two equations are known as the parametric equation of the curve, and these two as well, and these two as well. So two equations connecting three variables are called the parametric equations, and the subject of the equations must be x and y, and the third variable should be either theta or t, like in these examples. Gradient of the parametric equations. When both x and y depend on theta, then this is the formula of the gradient: dy upon d theta, dx upon d theta. When they both depend on t, then this is the formula of the gradient: dy upon dt, dx upon dt. Example. So we have these two equations, parametric equations of a curve, and we need expression of gradient. For that, we first need to differentiate x with respect to theta. Since we have theta here, so we need to differentiate this with respect to theta. So the differential of x with respect to theta will be dx upon d theta, and sine theta will become cos theta. And the differential of y with respect to theta will be dy upon d theta, and cos theta will become minus sine theta. This is negative sine theta. So first write the formula. This is compulsory. Always mention the formula: dy upon d theta over dx upon d theta. Write this here and this here. That's the final answer. Second example. X is equal to ln this and y is equal to this, and we need the expression of gradient. For that, we first need to differentiate x with respect to t. So when you will differentiate x with respect to t, you will get this thing: dx upon dt, 1 upon this, and the differential of this should be here. This is the simplified form of this. So when you will differentiate this, you'll get this thing: minus 5 upon t square. Now you need to substitute these two results into this formula: dy upon dt here, dx upon dt is here, and that's the final answer. So these are the two important examples of parametric equations. Next example. You all know sine theta, sine square theta. This can be written as sine theta whole square. So the question is, find the equation of the normal to this curve at the point theta pi by 4. So first you need to differentiate x with respect to theta, and you have to write this as sine square theta, sine theta whole square. So when you will differentiate x with respect to theta, you will get this thing: 4 sine theta cos theta, because this function is composite. And this is simple. The differential of y with respect to theta is dy upon d theta, and the right side will become 2 sec square theta. Now this is the formula of the gradient of parametric equations. Write this here and this result here. You can write sec square theta as 1 upon cos square theta. So this will become 1 upon 2 sine theta cos cube theta. Now you just need to put pi by 4 here and here. make sure you write cos theta cube when you will substitute pi by 4 here, like this. So the answer of gradient is 2. So the answer of the gradient of normal will be minus 1 upon 2. The inverse reciprocal of this. Now equation of normal. For the equation of normal, we must have both x and y. For that, we need to substitute pi by 4 here first and then here. So when we will substitute pi by 4 here, we will get this thing. And when we will substitute pi by 4 over here, we will get the value of y. So this is x and this is y and this is the gradient. So this is the equation of normal. You can take the screenshot of this if you want. Next example. A curve is defined for this domain and we have to prove this gradient. So we have two options to differentiate this. Number one, we can simplify this. We can convert cos in the form of sine like this. Or number two, we can use UV rule. You have option, you can use any method. I've done this question with both the methods. So the differential of x is dx upon d theta and tan theta will become sec square theta. Now here we have two options. This is the option number one. Converts cos square theta in the form of sine square theta, 1 minus sine square theta. This is the simplified form of y and this is the gradient of y. 2 cos theta, this is composite. 3 will multiply with this minus 2 and this 3 will become 2 and this should be copied here and sine theta's differential is cos theta. Or you can use UV rule if you want. So according to UV rule, this is the second method. You need to copy u here and you need to differentiate sine cos theta. Sine theta will become cos theta. Then this is v and this is u prime. So this is according to UV rule. And this is the other way to differentiate this. So you can use any method. This method is better. Well, this is the formula of the gradient of parametric equations. You should substitute this thing here and this thing here. And now you just need to use trigonometry. You have to give your answer in the form of cos. So you just need to, number one, substitute this sine square theta by 1 minus cos square theta. And you need to convert this in the form of cos square theta, maybe here or later on. First simplify this, so that this simplified form of this is here. Now you can write sec square theta as cos square theta here, which is this. This has become cos square theta, and that's the final answer. You can take the screenshot of this, or you can review this if you want. Well, question number 27. The next question of my book, practice book. Again, we have to differentiate parametric equations to get this answer. So first we need to bring this here, because whenever we have constant in numerator, we always bring the function in numerator, like this. This is composite, so make power coefficient, subtract power by 1 and then differentiate this. You all know how to differentiate composite functions. We already have discussed this in detail in my first lecture of differentiation. So this is a simplified form of dx upon dt. Let me first correct this. I'm sorry. This should be d. This was by mistake. This should be t. Because the function is in the form of t. Well, so differential of this, first copy this function, composite way function, so copy this here, make this power coefficient, subtract this power by 1 and tan differential is sec square t. Now you just need to substitute these two into this formula, like this. Now bring this in numerator. When you will bring this in numerator, I'm not bringing this in numerator, I'm basically writing the reciprocal of this, which is cos square t. So when you will write the reciprocal of this, it will become cos square t. You have to bring this in numerator. When you will simplify this, you'll get this thing. Now hence show that the equation of the tangent would be this. Remember, the point is not given. x1 and y1 are not given. The coordinates of the point are not given. So when the point is not given, then always treat this x and this y as x1 and y1 for the equation of both tangent and normal. So this will be x1 and this will be y1 for the equation of tangent. See, this is the equation of the tangent. So this is y1 and this is x1 and this is the gradient. Now multiply sine with both. When you will multiply sine with both, you'll get this thing. Now bring this tan on right hand side and write this in this way. Sine upon cos t and 1 upon cos square t. This in this way. Because we need tan here. Because we need our answer in the form of tan and sine. So first write this as this. Sine upon cos t and cos square t should be 1 upon cos square t. Now this will become tan. Now you can take tan theta common from these two, like this. See, this is the identity. 1 plus tan square x is sec square x. Therefore, when you will bring this on right hand side, you will get sec square minus tan square, which should be 1. So replace this by 1 according to this identity. Hence shown. This question is very important, especially the second part, this part. X and y1 were not given. The coordinates of the point were not given, so I substituted or considered this as x1 and this as y1. And I use this equation for the equation of tangent. And make sure after this step, check the this answer. Since you need your answer in the form of tan, so make sure you must convert this in the form of tan like this. And then just take tan t common and then replace this by 1 with the help of this identity. Hence shown. Next question, a very important question of parametric equations. Well, this is x1 and this is y1, and we need dy upon dx, and both functions are composite. So write this as cos t whole power 4 and write this as sin t whole power 4. Now differentiate this very carefully. First copy the function here because this is composite, then make this power coefficient, subtract this power by 1 and then differentiate cos. This will become minus sin t. This is the simplified form of dx upon dt, and do the same thing with this dy upon dt. Again we have composite function. So copy this sign here, make this power coefficient, then differentiate this sign and subtract this power by 1. Now substitute both into this formula, and this is the gradient, and this is the most simplified form of the gradient. You can leave your answer here or here. Make sure you must use this in the later part while finding the equation of the tangent. Don't use this in the later part. We need equation of tangent. We need to show equation of tangent, this one. Again, we don't have the point, so we will consider this as x1 and this as y1, and we will take this gradient. We will not use this, we will use this. Whenever you find equation of tangent or normal, always use this. Never use this. This will make the calculations complicated. So this is the equation of the tangent. Y minus y1 mx minus x1. Now do cross multiplication. Multiply this with this. So you'll get this thing. When you will multiply this with this and this with this, you'll get this. See, in your answer you need x and y on left hand side. So you need to bring this on left hand side and you need to shift this on right hand side. When you will do these shifting, you'll get this thing on left hand side and this thing on right hand side. Now you have to take common on right hand side. a sine square cos square t is common. And this is the famous identity. Cos square plus sine square is always 1. So this will become 1 and you will get this thing. And this is what you had to show. You can check the solution again, because this question is very important. This is one of the best questions of parametric equations. Part 3. Hence show that if the tangent meets the x-axis and the y-axis, this tangent, if this meets the x-axis at P and y-axis at Q, then we have to show this. OP plus OQ is A. See, if any line cuts the x-axis, then the coordinates should be x comma 0, and y for y-axis coordinates should be 0 comma y. So we will first substitute these 2 points into this equation to get the coordinates of P and Q. So by substituting this point into this equation, we have x, a cos square t. Similarly, we have y, a sin square t, by substituting this into this equation. Now we need distance OP. O means 0, 0 and P means this. So by using distance formula, we have this thing. OP is this. Similarly, OQ is this. So when you will add these two, you will get this thing. A cos square t plus a sin square t. After taking a common, you have this, and this will become 1, hence shown. You can check the solution. First get the coordinates of P by substituting this into this equation, and then coordinates of Q by substituting this into this equation. These are the coordinates of P, and coordinates of Q will be this. Q 0 comma a sin square t. So the distance OP is this and distance OQ is this, and you just need to add these two. When you will add these two, you'll get this thing on right hand side. This will become 1, hence shown. Now this is one of the most important concepts in parametric equations. The second differential of parametric equations. The second differential, mean d2y over dx2 of parametric equations, is always implicit. See, if this is the first differential, dy upon dx, now notice this, x and theta, so this is implicit. So when you will find second derivative, you have to multiply your answer with d theta upon dx because of the implicit function. This is implicit. So whenever you find second derivative of parametric, if the function is in the form of theta, then always multiply your answer with d theta upon dx. Or if the function is in the form of t, then always multiply your answer with dt upon dx. See, if the question is find the second derivative of this, you have got this from the parametric equation like this. So this is implicit. So make sure when you will find second derivative, you must multiply your answer, this answer, with d theta upon dx. Like this, because when we differentiate y cube with x, we always multiply our answer with dy upon dx. I mean, we write this thing here like d theta, so d theta, and x, so dx, as we used to do in this. We have y here, so dy here, and dx should be here. See, if the question is in the form of t square, so when finding second derivative, must multiply your answer with this operator. dt upon dx. This is the way to make the operator. This variable should be here and this variable should be here. What if you are differentiating theta power 4? Must multiply your answer with this. d theta over dx. This is the way to make the operator. inverse trigonometric functions.